The broadcast is now starting. All attendees are in listen-only mode.
Starting the session. Can we start?
You want me to wait?
No, can we start the session?
Yes. You want me to start immediately, or you want people to join in?
People are joining. We can start the session.
If you have more than 10 people, you can start. Speakers should be here.
Oh, I think you will attract definitely a crowd beyond 500, and I can assure you that much. This is one technology which
I mean, in these uncertain times, if they don't listen to quantum, what would they listen to?
Absolutely, and I am personally intrigued myself by this, and therefore I personally am going to sit through and I'm going to learn. I did my engineering many years back, and since I have never been back into technology, and so I'm a student here for all of you, and with years which are going to hear absolutely. So Professor Ashutosh Sharma, Secretary, Department of Science and Technology, Government of India, a very warm welcome to you. So thank you very much for joining us this afternoon. Professor Manas, Dr. Rohini, you help us balance our gender. Thank you so much. We're proud that you're with us. Sesh, a colleague from IBM who's sitting here. As I sit in Bangalore, he's also in Bangalore. I'm kind of stuck here because of the COVID. I traveled here for a day, and then lockdown came and I could not come back to Delhi since. Our chairman for ITes, eCommerce, my lovely friend Lovneesh, Chanana. Thank you so much, all of you, for joining us this afternoon. I think it's the most timely discussion that needs to be done. Technology is the way forward. If you look at the way the world has been hit with COVID, I think every business model has, if I may dare say, has failed. And none of us had ever imagined something like this. No business plan in the world had ever factored in a disruption of this nature and size. And therefore, obviously, what is in front of us is an unimaginable task. Each and every country, each and every human, each and every business job is impacted. You see a lot of people impacted across the world. I think if the Honorable Prime Minister's Digital India had not started 6 years back, I and you would not be talking like this. We would have not been transacting our business. IT companies would have never been able to solve the problems of the world the way we have done. Today, we are respected in the world because we did not fail. That's because of Digital India. That is because of the infrastructure of technology that we have built and weaved around ourselves. And I think all of us need to be proud of that. Work from home is something that is going to stay. While I have been here in this chair for about 65 to 90 days, I think I brought my office back at home, and I don't know how to deal with that right now. So that's another space that we need to learn how to deal with, because it just doesn't end. It just keeps continuing from the morning to night and every day of the week. So that's another thing that we need to learn. Our stock markets work, our banks work, our e-commerce have expanded. The way people consume has changed. What people consume is changing, and therefore each and everything is leading us into how behaviors are working, how things are behaving, and therefore technology as a backend is what is an adoption for everybody in the clear case of that. I'm just going to dive in a little more because I come from the business side of it, and I would like to just share with you as to how we are working at ASSOCHAM with the Government of India, the business and the global industry. I think the demand for products across the world has been hit terribly. However, there's a very positive thing that has just come through in India, and I would like to share this with you. And a lot of steps that the government that have taken are in the line, and it may sound a little advanced, but I think the business in India is going to return very quick, much sooner than later. And let me pull the case for that. 14% of agri-economy, which supports 49% of the business and the jobs, is not impacted. And the impetus that the finance minister and the prime minister's view has been that, you know, the rural economy is robust. I was looking at the numbers of Mahindras, and obviously this is not technology, but this is mechanical technology. The farm mechanization has grown by 2%. You see clearly two-wheelers are going to grow. So therefore, what one is saying is that rural economy is intact. There's been migration of people. You're seeing FMCG products are being consumed more in rural areas than in the urban areas. Obviously, the consumption has moved there. So what is really happening is that the rural economy is intact, and therefore we will come to quantum and how quantum will help us, and I'm sure all of you will provide that solutions. 60% of the services industry has been hit, but not beyond repair. So maybe the travel, tourism, restaurant industry is hit, but eventually we are going to come out of it. It's not a damage beyond repair. there is a lot of hit that has been happened in the manufacturing side of it, and especially the 25% of the GDP which is manufacturing, and out of which 85% is MSMEs. And ASSOCHAM is working with Government of India, and I think there are two left requests that are, because whatever we had put, government has agreed and has implemented. The two of them are one-time rollover of all loans for all cross sectors, so that there is enough cash flow that comes back and there is no pain in the system left for the MSMEs, and they are able to restart their businesses without having to worry about liquidity, which is right now the most crux thing. And this, another thing which in India is the demand side of it, and the demand side of it is something which I'll again go back. When the rural India is up, the services industry is up, the per capita of this country is $2,000, and if $2,000, 75% of the $2,000 is essential buy. When essential buy is going to return for 130 crore people, you can very well imagine the demand is coming back much sooner than later. And if the government cuts GST by 50% at this stage, you will help spur demand much more, and you will front end the whole thing. And therefore, that's the piece that ASSOCHAM is taking. And that's, I thought I will share with the audience. I thought I'll use your presence as well, Secretary Saab, so that I can share this view of ASSOCHAM as well. I think quantum computing is a real is the area of computing focused on development of computer technology based on principles of quantum theory. We are looking at solutions. We are looking at answers to things which we have never found answers to in the past. India has clearly been lagging in this space for a while, and some measures that have been taken by Government of India in the budget, they have allocated $1 billion+, which is about 8,000 crores for us to start working with over the next 5 years, is a step forward. I think they announced a national mission on quantum technologies, which is now housed with DST, is now given the responsibility to focus. The mission's focus is obviously going to be, we would listen more from you on the fundamental sciences, the translation, the technology development, human and infrastructure development that one is talking about, the innovation and the startup ecosystem that needs to be created all around this. Anything that would happen has to have a purpose, has to have a target, has to have a start date, has to have a close date. So I would say that it's very, very heartening to see that, you know, the mission is trying to build a 50-qubit quantum computer in next to 4 to 5 years, and it's something which is going to be very, very great to see. DST had started in 2019 the Quest program with funding from itself. However, now you see success that Quest 2 is in pipeline, and that's very heartening again. So you see progress that is coming through. There are a lot of technology papers that are being shared by our people across the globe. I think it is time for us to benefit from this and draw out applications. The world knows there is opportunity in this space, and therefore everybody is investing manpower, money, time, so that they are able to come out first out of this. So anybody who comes out the first solution would have the mover's advantage, and obviously will lead the technology going forward. It is an emerging field of, I think, of physics and engineering, and a lot of work has been done, but I think what is more important today is working on solutions and applications. India would obviously look at strategic applications of this, but there's a place and time where we should also look at this applications in the space of pharmaceuticals, healthcare, agriculture. I'm made to understand, sir, if this is done well, instead of 10 years time that one takes to get a drug to the market, it could be done in 2 days. I mean, that's the kind of cycle time that one is trying to talk about. We could do gene testing. You could do any kind of stuff, which is airplane simulations could be done in matter of minutes, which would eventually actually take such a long period of time. And therefore, I may dare again say a lot of business models and the landscape for multiple businesses is what is going to change if you really look at the whole space of quantum that one is trying to talk about. I'm going to listen to you people. I'm going to learn from you, and I'm sure so many of us as delegates are here to understand from each one of you. ASSOCHAM is truly delighted to host this. I think there are people from across the globe who are going to come and share their views, their perspectives, their experiences for all of us to learn from each other. Professor Ashutosh, thank you very much once again. Thank you all of the speakers who have joined us this afternoon, and we look forward to hearing from you. May I now invite, technology plays a role, so I'm sure all delegates have looked at your profiles, and therefore I'm not going to use the time to introduce people. So those who have not, may I request them to, everybody's on LinkedIn, and quickly glance through them. May I now invite Shesh to address us with his views, please. Thank you.
Hello all. Can you see my screen? Can someone confirm?
Yes, please.
Okay, great. Thanks, ASSOCHAM, for the opportunity. I'm going to talk about quantum computing and IBM Quantum and also what it means for India. So here is the picture of the actual machine that's there. This was what we call a system 1, just to give a sense of the sophistication involved in this technology. What you see here is the form factor that fits into a data center. It actually now resides, a lot of these machines resides in data center in Poughkeepsie. What you're seeing here is a chamber, which is a vacuum chamber, and inside which is this dilution refrigerator, the canister type thing that you're seeing. And then inside it, if you open the canister, is this multi-level refrigeration unit that you see there. It's basically trying to get the temperature down. What it operates on eventually is at the lowest level is 15 millikelvin, which is the smallest temperature that we have achieved. 15 millikelvins, just as a context, is roughly 100 times colder than outer space. The actual hardware sits right at the bottom. It looks like a regular microprocessor. The technology that we use is a superconducting qubit technology. It's something like this big, and it sits in the PCB, and then it goes right at the bottom. On the right is the control mechanisms to send a signal in and pull the signal out. This all sits in the data center, and the user programs through cloud framework. This is the physical hardware. It understands signals in microwave, and that's a very physicsy thing. You would want a software stack that built on top of it. The software stack is called Qiskit. The hardware, think of hardware is right at the bottom, the picture that I showed you just now. And then you have the software stack built on top of it. The Qiskit has many modular layers. The lowest layer is the Terra that can talk to the hardware, and eventually it can map to different kinds of hardware. And then we also have the higher level of abstraction called Aqua, where all the details of the quantum physics is abstracted out. It becomes essentially a Python library. So it is an open source Apache 2.0 license, open governed library framework through which you can program the hardware. So how does it work? So I'll just show you a quick video. So here is the person sitting in their laptop programming through, say, a Jupyter notebook, sends the program across. It goes through the network onto a particular classical hardware. So in this case, they are sending out an operation, which is a measurement operation. It's going through this internet, and then it's going to hit a regular server, which then sends it across to the control mechanics here, which then will send the control signal into the actual hardware. So these are the microwave signals going in. It's supposed to do the measurement. When we do measurement, we are collapsing the state essentially to reroute bits in zeros and ones instead of quantum information. And it's going to go down to the hardware, perform the operation, get the signal back through the control mechanics, and then it comes back to the user who's sitting right here in their laptop. So this is the classical cloud model. Essentially, it works out that way. And eventually, it's going to work in the cloud space as well. This has been immensely popular in terms of usage. I'll show a quick video of it. So what you're going to see now is the data from the last 4 years. IBM put out these machines on cloud in 2016. A lot of these machines have been for free usage. People can go program it on hardware, write their programs through Python and program it and run their programs and get results back. What you're going to see is on the x-axis is the time. It's not quite visible, but the real data set is how many people are running their experiments. The top right, you're going to see is quantum chips, the actual experiments that are run on quantum hardware. There is also quantum simulators that you can run your experiments on, that you have the data on here, and then the number of unique users that are there. And what we'll also see in the map is where did the particular experiment came from, so you get a profile of where these operations are coming from and who's doing these experiments. So let me quickly run this. So you're seeing the data set coming through. The blue is initially less number of actual experiments were done, but they were actually in millions already. A lot of work happened on the simulation front initially. We are now in 2017 timeframe. Now you're going to see that the actual hardware is being used a lot more. Now getting into 2018, you can see that the hardware experiments are dominating. In terms of where the experiments are done, you can see the eastern seaboard of US and Europe are quite active. India is also quite active, as is Japan and Australia. You can see that well over 100 billion experiments were run. This is data till October 2019. So we have another 6 to 8 months. So I'm imagining it will be 150 billion plus experiments would have run on actual hardware thus far. 190K unique users have been using this hardware through this time, in the 4 years that these machines have been there. So you can see that India has been quite active, which is a heartening thing, but I think a lot more needs to be done. Hopefully the initiatives like Quest and other things will push these things even further for us to adopt this technology more. All right, so IBM has a Q network where there is a lot. This is the engagement models that we have. A lot of academic and industry partners, a lot more academic partners, along with startups and industry partners across the board. We crossed over 100 partners, 10 industry partners with multiple hubs. Hubs are essentially research institutes or research labs that can partner with others to do a lot more research of their interest. Okay, so how do you think about quantum? Why is it interesting? So this is a cartoon that essentially shows how to think about it. What is shown in the white bubble called easy problems. These are easy for our regular computers of today. Light blue shows the hard problems, problems that are very hard to do in our regular computers today. What quantum is doing is opening up a new frontier, new space. This dark blue that you see, what is called as quantum possible, or the kind of problems that you can do efficiently in quantum. What is obvious from here is this is over and beyond what is easy in the current hardware, which makes it exciting. What is also to be noted here is it doesn't mean it's panacea. It doesn't mean it can solve all hard problems. There are certain class of problems it can do efficiently, and those are the problems that are relevant. The hard problems there are going to be hard problems that are going to be hard for quantum as well. But what is interesting is the space this is opening up. This is an active area of research, and frontier is moving as we speak. So what is a qubit and compared to classical, and why it is interesting? So a qubit is different from classical at a very fundamental level. Classical bit can be state 0 or a 1. What is quantum bit or a qubit is that it can be in both 0 and 1 simultaneously, and that is in probabilistic sense. Imagine that you can be in any part. This is called a Bloch sphere. It can be in any place on that external sphere, not just at the North Pole and the South Pole. All it will do is it will change your probability of being in 0 or a 1. So what you're done essentially is when you're honoring the rules of quantum mechanics, you're moving away from something that is fundamentally deterministic to something that is fundamentally probabilistic. It's a fundamental shift in the way the basic elements are being represented, the operations are performed. So take an example of caffeine, for example. If you think about simulating a simple molecule like caffeine, which has about 24 odd atoms, if you want to simulate this exactly in a quantum mechanical way, you can do it. If I had 160 clean qubits, I could simulate this efficiently. But if I want to do it in a classical hardware, I would need something in the order of 10 power 48 bits to represent a state in that particular framework. And 10 power 48, just for reference, it is estimated that total number of atoms on planet Earth is roughly 10 power 49 to 10 power 50. So what you're essentially asking for is roughly 10% of all atoms on planet Earth just to simulate one simple caffeine molecule, which is essentially saying that it's practically impossible. So why is this happening? What is interesting in quantum is that as you increase the qubit, the state space, the number of representations that you can hold in that state because of that simultaneous representation of being in both 0 and 1 expands exponentially. It grows like 2 power n. So for instance, if I had 2 power 10, I can represent 10 qubits, I can represent 1024 different states. It holds that many state spaces. And what also happens is if you are in the superposition state, you can perform those operations simultaneously across multiple states in parallel. That's where this parallelism or effect of getting the compute advantage takes in. So a good algorithm would be one that would leverage the state space effectively, do the transformation in the state space, and then use interference to converge on the right answer in a probabilistic sense, and then get the result out. So because of this scaling behavior, what that does is that you can solve some of the problems that are very hard to do classically because you're leveraging this exponential state space that's available. One unfortunate thing with popular press is that equating qubit with the power of a quantum machine. There is more to it than just qubits. Qubits are important, qubits are vital, but then qubits are not sufficient. So the 2 power n that I mentioned is the potential state space that a qubit could offer. But in reality, when you build a hardware, how noisy or how clean it is very relevant, or else you're not going to access all those exquisite states that may be out there. How much of those state space is accessible essentially is what this new metric called quantum volume captures. In effect, think of this as something like floating point operation per second, which we use many a times in measuring the power of a supercomputer, etc., like petaflop, so on and so forth. Think of this as an abstract metric that combines multiple metrics that, along with the number of qubits, also looks at the noise and other aspects in the system and comes up with this metric. It's a mathematical equation. The reason I bring this up is that just increasing number of qubit is not sufficient. How good that qubit is equally important. So in this cartoon, what it's showing is, if you just go from 50 qubit to 100 qubit, just double it, and you don't touch anything on the error side of it, you're not gaining anything in terms of your power of the machine. If you, on the other hand, improved your error rate by an order of magnitude, you get a 500x improvement in so-called quantum volume. So what we ideally want to do is to move across the diagonal so that you maximize it. So quantum volume essentially tells you of the total state space that's available, roughly what amount of state space is accessible to you. You would want to access all those states that is available for your quantum to leverage the whole power of it. So then you can ask the question, how is it scaling? And this is where it gets very interesting. On the left is the scaling of quantum volume.
You got 4 more minutes.
All right. Okay. So on the left is the quantum volume that is increasing. What is important is that it's increasing exponentially in the last 4 years. What is called as Gambetta's law is essentially that the power of the quantum hardware, quantum computing power, is going to double essentially every year. This is very similar to what was eventually called as Moore's law, where the doubling happened in 1.5 to 2 years, and this was the paper that Gordon Moore wrote in 1965, and it looks eerily similar. What we think is that we're going to be on this curve for some time to come, and this roadmap is likely to continue for some foreseeable future. So I'm going to go into the applications of it. There are many applications of this. Given the limitation of time, I'm going to focus on one aspect of it. There are 4 different categories where the applications are likely to emerge in the short run, which is the horizontals here, the simulation type things, chemical simulations, the scenario or Monte Carlo type simulations, the optimization, and the AIML. Given the situation that we are in right now, I'll just focus on one aspect, which is healthcare and life sciences. There is a lot of interest in healthcare and life sciences because a lot of problems there have computational complexity that are very hard to do. And the scaling behavior of existing algorithms are not very great because of the limitations like the scaling of those algorithms that naturally exist. So the kind of problems it's likely to address are broadly 3 categories: the diagnostic assistant type problem, precision medicine class of problem, and pricing. In assistance problem, a lot of customized targeted application of medicine is something that's picking up a lot. In terms of diagnostic, you would want to be able to automate the process of identifying various diseases through medical images. There are multiple aspects of imaging recognition is needed, like CRT, X-ray, and whatnot. Doing a better quality prediction of these images to exact diseases, it's always a challenge, and especially with complex imaging, multiple images and across the board with noise and so forth, it becomes harder and harder. Potentially quantum can produce a better result there. And also biomarkers. Sorry, was there a
You would
question?
like to conclude, please?
Yes. Okay, and I'll just leave this chart, and I will also mention that healthcare, health pricing, and in terms of doing insurance and other aspects could also benefit from it. So can drug discovery part, which could be a significant aspect because that's very hard to do in terms of computationally these days. Just to summarize in terms of what India can do, India has done a good job thus far in getting a lot of people out of poverty and also moving away from moving towards more middle income nation. If we want to get the next jump in terms of per capita and moving up more people out of poverty or doing more things in the society, we have to embrace the latest and potentially disruptive technology. Got to move up the value chain and have to think of becoming a technology leader. For that, we got to invest in this technology and leverage this. There is a window of opportunity. However, major players across the world are investing quite significantly in this technology, which means that the window of opportunity is limited. We got to grab it when it's available. And there is a big rush to figure out who will be the technology leader of tomorrow. What is also interesting in this technology, as I mentioned with healthcare example, is that not only can you invest and leverage and become a technology leader potentially, but also the kind of problems that you can address can benefit people and can benefit society and can benefit population as a whole. And there is a twin side to this, having the skills to develop it and also apply it in real world, the kind of problems can address has real meaning to people in this country. And also a last comment on jobs and future, the next generation coming through. This technology is estimated, at least one report estimates that it's going to be something in the order of $5 billion by 24-25. And by end of the decade, it's likely to be around 25 to 50 billion. And another 10 odd years, it's going to be in the order of $450 billion plus. So if the next generation coming through our education system needs to find jobs, it's better to have some skill set in this space. And just to highlight the IT industry, it's been one of the important players in this growth story of India, especially in the per capita income in the last 30 years, with a deep roots in its impact, with 8% GDP and so on and so forth that you see here, and nearly 4 million people employed in this particular space. For the next generation to find jobs and also to do research and also to open companies, this is a space to look out for. And this is an opportunity and something that India should seriously consider. Thank you for your attention.
Thank you very much, Shesh. Professor Ashutosh, would you want us to make a little change in format? Are you okay with this format of presentations of companies the way they're following? Is it a particular thing that you would like to listen, or?
No, it's perfectly fine because we have about 8,000 crores riding on it, so I better learn something. I'm perfectly okay hearing this.
Perfect. Thank you so much. There are a lot of things that I liked, Shesh, what you spoke, and a lot of them were bounces. And normally when I used to play cricket, I used to let them go. But I'm going to definitely learn this much more than I have known in the past. So let me ask the lady of the afternoon, Rohini. She's from Microsoft, and Rohini, let's see what you have to say. Thank you so much. Rohini, you're on mute, so it will be nice if you can unmute yourself.
Yeah, can you hear me now?
Yes, that's perfect. Thank you so much. I'm going to put myself mute as well as put off my camera.
Sure. So first of all, thank you very much for the opportunity. It's a very exciting space, and thank you, Shesh, for the original initial comments. In some ways, there will be some parts here that might be repetitive, and I might just go faster on those areas. I want to spend a little bit of a time on the promise of this area, and I think let me just start with a video, and I hope you can see this because it gives a perspective as to where we are.
We talk about quantum computing, it's a completely different game.
Quantum computing will enable us to solve problems that currently take longer than the lifetime of the universe in seconds, hours, or days.
We completely reconceive the space in which we do computation.
Quantum computing is like going from crawling to going to a different planet. It's different.
It's only natural that we would want to use the world's most powerful device to combat the world's most challenging problems.
We can detect global warming.
Maturity.
What are the boundaries of machine learning?
Fighting diseases. The possibilities of quantum computers are endless. Microsoft has the best and the brightest working on this problem.
It's really happening. Progress is very fast. We're building a quantum computer.
What the world wants to know is what happens when we turn the machine on.
What problems will be solvable with a computer that computes in a billion parallel universes at the same time?
So as Sesh said, I think the race is on. And clearly the area of quantum computing has a lot of attention that you will see, and I will also talk about this primarily quite a bit in my conversation. But I think the areas which are broadly part of quantum as a technology, which are also very exciting, are beyond just computing. I think the area of quantum communication, the area of quantum cryptography, quantum key distribution, those are also areas which will become important. Clearly, there are linkages between them, but quantum communication is another area that I think would be very exciting. The third area is that of quantum sensors. That is using the effects of quantum mechanics, sensors that use those kind of effects to detect signals that would otherwise be impossible. Think about variation of gravity around the Earth's surface because of various changes that happen in the tectonic plates or the movement of the oceans. So some of those very, very highly sensitive sensors can be built using quantum mechanical phenomenon. And finally, the point about quantum simulation. And I find this extremely exciting because one of the favorite quotes that I have from Richard Feynman, and I'll just play that out. So this is one space which is very exciting, but we will spend time on quantum computing. But the quantum simulation quote that I wanted to share with you, and I love this so much that I could not hold myself, that what Richard is saying is nature isn't classical, and so if you want to make a simulation of nature, you better make it quantum. And by golly, it's a wonderful problem because it doesn't look so easy. I love this quote. So we will spend some time on quantum computing because that's something that obviously Microsoft is interested in, just like IBM and many other big players. So quantum computing, clearly, what is the history of it? And I won't play this particular point, but
there was a time when the newspaper said that only 12 men understood the theory of relativity. I don't believe there ever was such a time. There might have been a time when only one did, because he's the only guy who caught on before he wrote his paper. But after people read it, a lot of people kind of understood the theory of relativity in some way or other. But more than 12. On the other hand, I think I can safely say that nobody understands quantum mechanics.
So I think with that disclaimer about quantum mechanics, and I've been fascinated with this field for several years now, and in fact have some history going back to my early days at AT&T Bell Labs, where in fact Love Grover was working in my lab, and little did we realize at that time the kind of work Grover's algorithm being so fundamental to quantum computing. So it's an amazing time to be here and see the space getting more attention. So what is a quantum computer? As Sesh mentioned, it is a machine that is using the laws of quantum mechanics to do calculations and at the subatomic level, and something that Richard Feynman proposed in 1982, but clearly a lot of work has happened since then to bring it to reality. And what does that allow us to do without going too much into it is that clearly the kind of problems that you can simulate for small number of atoms, which require classical computers, which may require as long as the age of the universe, are then solvable potentially with a quantum computer, given some of the challenges that Sesh talked about regarding the stability of qubits. But the race is on, and all major players and governments around the world are looking to move in that direction. And the kind of problems that the promise holds, right, are ranging across the board, whether it's from material sciences to global warming, for carbon capture. How do you make fertilizers? Because nature seems to know how to make fertilizers. Bacteria are there which are able to fix nitrogen from the atmosphere. Can we do that and have better fertilizer, more efficient fertilizer production that is more energy conserving? And of course, machine learning. So in a way, the race is on. But what Microsoft has done is taken a somewhat more a unique approach. There is clearly a huge effort that's going on into the hardware side of quantum computing. But at the end of it, to be able to utilize quantum computing, you're going to need a full stack. And that is where Microsoft is spending time in terms of building the right bits and pieces together. So I'll ask you to, in terms of the kind of broadly the approach that I mentioned to you, so there is clearly a team that is working on quantum and also looking at stable qubits, and we've taken an approach which is called a topological qubit approach, which we do believe has advantages in terms of its stability. It is a complex problem, but there are people with a lot of excitement and potential working on it. But in the meantime, we are from a Microsoft perspective believe, as I said, that while the quantum computer is being developed and more stable qubits and the whole quantum volume is being addressed, how do we make sure that the ecosystem is being ready to be able to solve the problems which are out there, and some of which can be addressed today, especially using things like quantum-inspired algorithms or quantum simulations.
The Microsoft Quantum Program is a global scale program focused on enabling commercial scale quantum computation. It's really about bringing quantum impact to people today and tomorrow.
Quantum computing has the opportunity to make an impact on the world right now in a revolutionary, game-changing way.
We're focused on developing every element of the quantum system, an end-to-end full-stack technology from the algorithms to the software stack to the hardware itself. To reach a commercial scale quantum computer, it requires revolutionary discoveries across physics, computer science, mathematics, material science,
all of which have to come together to make topological qubits and multi-topological qubit systems. We have a team that's spread across 8 labs around the world. Although we're spread out, we are one team working towards one goal.
Building a quantum computer is a huge task. It's all the way from the software all the way down to where we control the quantum states that makes up the qubits.
Here in the lab, we have fabrication technologies, nanotechnology that allows us to turn the dumb materials into smart devices.
The Microsoft Quantum Program allows us to dream big. We need to dream big.
Azure is the world's computer. You have access to the tools, services, and solutions in a very familiar environment. And with Azure Quantum, we're bringing quantum solutions forward to that environment. We're bringing quantum impact to your fingertips. We're working with enterprises and companies around the world, energy optimization, risk and financial analysis in medical diagnostics, to identify where quantum solutions will bring about impact to their businesses. A great example is Case Western Reserve University.
We're working with Azure Quantum to optimize the way that people get MRI scans. Patients have access to faster and better MRI scans in a way that wasn't possible before.
We can make those scans up to 3 times faster by using quantum solutions on classical hardware today.
The really high-level scientific goal is to be able to solve problems that we can't solve today.
Azure Quantum enables every developer, every person, every enterprise to really tap in and succeed in their businesses and their endeavors with quantum solutions. And that's incredibly powerful.
So the approach we have taken is to have a really full stack view, as I was mentioning earlier. And what does that mean? That means that we are bringing partners together who all have pre-built solvers, particularly domain-specific solvers, let's say chemistry-related packages, simulation tools, resource estimation tools, while quantum hardware options are there from both Microsoft as well as a set of partners. Because at the end of the day, it's going to take that full stack to be able to leverage the power of quantum. And as I was mentioning earlier, there are algorithms today that are quantum inspired that can leverage the thinking that goes behind a quantum system to be able to solve some of the large optimization problems that are today and very much within reach of some of the research work that's being done. So what does it mean? For the full stack approach, as I mentioned, the application areas are all the way from, as I said, optimization, some of the large, whether it's traffic or it's financial systems, or any other kind of large-scale optimization problems where you're looking at searching through a large state space. Machine learning is a big application area, and of course simulation. So it's a full stack approach which brings in software tools and services, as well as classical hardware, because you can simulate quantum on classical hardware with FPGAs and some of the large high-speed GPUs that you have out there, while the quantum hardware, both the topological one that you saw in the video, which is an area of research, while we are working with some of our partners like Honeywell and others to bring in hardware that they have out there as part of the overall stack.
Dr. Rohini, got 4 minutes?
Yeah, sure.
Thank you.
So what does it mean for people today? And I'm going to move fast because I do want to leave with the idea that given the kind of problems you can solve today, and the need for people to skill up on thinking about quantum, because as Dr. Sesh also mentioned, this is a very different way of thinking about computing. It's a paradigm shift, and it does require people to go back and learn about the linear algebra, learn about quantum physics, and think very differently in terms of how they code their algorithms. Therefore, the thinking we have is, how do people in India today prepare themselves for the quantum world? So the thought I'd like to leave with is, are there opportunities today to learn, build, and contribute? And I would say yes, there's a lot out there that you can start to leverage today to learn this space, start to build, and contribute to open source repositories. So let me share a little bit with you. Q# is a Microsoft open source programming language for developing and running quantum algorithms. The whole idea is that it's designed from the grounds up for quantum development. It is integrated with most of the world's popular developer tools, and it's compatible across all of the Azure quantum endpoints, whether it's our own quantum simulator or third-party Honeywell, etc., quantum hardware, as well as going forward, any other hardware that comes forward, because this is an area which is fast-moving. And finally, like I said, it is future-proof, because when you build something today, it is ready for the future quantum hardware as it gets available. So the go-dos for the people in the audience in terms of preparing yourself for this space is, as I said, Q# comes along with the QDK, which is a quantum developer kit. It's a full feature development kit with standard tools and languages, quantum applications that you can develop, run in various environments, including, as I said, the built-in quantum simulator. So you are preparing yourself for the future. Quantum katas is, again, is a very, very rich set of open source self-paced tutorials that help you walk you through progression from foundational to challenging to learn quantum concepts while you also code them. So you're learning them, and this is available on GitHub. And finally, contribute to the open source community. There are 7 repositories on GitHub which are quantum computing related. Go there, contribute there and be a part of that community as well. So I would just leave with the audience to say, get started, learn. Microsoft has a lot of material on Microsoft Learn. Like I said, there are quantum developer workshops which are there. The place for you to go to is azure.com/quantum. Everything is available there in terms of both the developer workshop as well as all the other material I shared. So I think the big call to action is for the people out there to start learning this technology while the big quantum computers are being researched on. I'll stop with that. Thank you.
Thank you, Dr. Rohini. Thank you very much. You were bang on your time. You actually saved me a few seconds, so I will take a little of that. Sure. I think what is there for common people in this is what would be very, very essential for large masses to understand. I think there's a huge space for people to connect and understand as to what we are talking on a common platform, as well as a common man's benefit from this technology is essential. I think that one talks about these major problems of carbon emissions. So can we find solutions where carbon could be absorbed by some other material and the environment becomes a better? Lithium-ion batteries are an issue. Can we find a chemistry of something which helps us to find a better material which can be a better battery storage for us? So these are things that one was looking at answers from such technologies going forward. So thank you very much for what you shared. Let me now get Professor Manas. He's from National University of Singapore. Professor, so I'm sorry, you could join us and you can please start with your presentation, please. Thank you so much.
Okay, so thank you. Thanks first the organizers for the invitation. It's a very nice enclave. The reason is I see that I come from the other side, that's the academic side of things. So I'm coming from the Center for Quantum Technologies. And I would tell you not much about quantum computation, but a little bit deviated, which I would thank both Dr. Raghunathan as well as Srivathsa for introducing the general aspect of quantum technologies. So I can take it over from there. And I would also thank Professor Sharma for being here, because it's a big investment as India is looking for. And I think it would be a big jump from India's perspective into getting into the real stuff of quantum. So now what I'm going to tell you about is not much about quantum computation. I will come to that a little later, but I will mainly spend the time on what we mean by supremacy of quantum technologies in general. So this term itself can be seen in a different context. So let's take a look into the Quantum Manifesto. That's what the European Union came up with in quite a while ago in 2015. And that manifesto is going to run till 2035. So there it's spelled out in a very simple way that what is supremacy in a supercomputer cannot do in the whole age of the universe, but a quantum computer can do. And that's the target by 2035. So 20 years from the start of 2015. So that's a long journey. And I'm pretty sure that it's not a competition at the moment. It's more learning from each other, and it's a collaboration. And I will actually harp on that part, that it's a collaboration. And I will try to argue that, in fact, as quantum computers develop, the other fields like sensing and communication, as I will tell you a little bit more about those, they develop as well alongside with it. And that's the part I will stress all along by what I'm going to tell. And this is my perspective in the whole field as it revolves. Now I take another aspect of this quantum manifesto, which was the words were coined by Alan Aspe, and he mentioned about the second quantum revolution. Now, what was the first quantum revolution? As we know that we already use lasers and also transistors. They also are based on quantum mechanics. However, there are two important resources which we are presently brought under control. And those two resources are quantum superposition and entanglement. Now, these two actually gives us enormous jump in what we can actually do with these two new resources. So take, for example, that I have, in fact, a small computer, which is, I call it classical computer, CC, and I have a yellow colored ball, which goes inside this box, and it becomes a red ball. And if I continue, or if I have not been told what this box does, so what I need to do is I have to have two choices. One is yellow, the other one is red. So I put the yellow first, and I see that it becomes a red. Then I take the other one, which is the red ball, and again put it inside, I see it is yellow. So in order to know what this box does, the CC, I have to try it twice, one with the red and the other time with the yellow, in order to understand that this box actually flips the state of or the color of the ball. Now, in case of quantum, the situation is very different. I have a larger box, doesn't matter if it is a larger box, as long as it is more powerful, I'm happy. So what I can do is I can create a state which is, let's say, 70% about red and 30% about yellow. And I push it through this box and I see that it gets flipped. And this is exactly what quantum parallelism gives. And that was exactly what Dr. Rohini was mentioning about, or Raghunathan, about the power of it, that it allows you to exponentially grow the moment you add one more qubit. The other thing, and now this is a mathematical way of writing it, but never mind, doesn't matter much. It's basically the 0 is now our yellow and 1 is our red, and we can create a superposition of these two. Going through the box, we end up in flipping those weightages. Now, entanglement is a little bit more weird, and we don't see it in everyday life, and that's why it's weird to us. And it's of two particles, not any more one, but two, and they are in a particular state where one represents one of the particles and two represents the second particle. However, I have created a state which is within this box, which is one yellow and red plus a red and yellow with certain percentage. If you look at the mathematical structure of it, it's exactly the same as this one, except that I have two particles. There is no way by which I can write it as a state of the one particle, either with color red or yellow, and the number two particle with red and yellow. And that's exactly what is called entanglement, which allows us to have very, very strong correlated system. And this correlation is absent in any type of classical statistics. What is this correlation? So suppose I have particle number 2, and I measure it and I find that it is in red. The moment I find it in red, no matter where the particle 1 is, could be even millions of miles away, I would still end up the other particle in yellow. And that's what the power of correlation is, that once I have created a state like this, no matter how far they are, they will always be strongly correlated. And that's exactly what is used in quantum communication. Okay, so I'm not going to talk about communication or computation to a large extent. What I'm going to tell you about that superiority of quantum sensors have already surpassed the presently available classical sensors. And here, as was previously been said, that we would like to know any test example where it shows me clearly that, well, I have a machine which outperforms any classical task, which are important to any form of regular activity. And I'm going to show you that these two sensors are in a stage where you can actually deploy them. The reason why I did not talk about quantum communication is that, particularly quantum key distribution, QKD is already been deployed. It's already in translation. You can actually buy QKD systems. I'm more talking about those which are in the process of translation. And here comes the magnetic field sensor. Now, a little bit about how that works. Like in any quantum system, I have two levels here, the blue and the red. and in between there is an energy gap which is fixed as long as this qubit does not interact with anything else. However, the moment it starts to interact, suppose there is a field which is going through it as a background, the state starts to evolve. And what does it mean? Well, don't bother about what is written here. What is important is that we can measure this delta phi, which is a function of time, very well. And if you can do that, here comes the application of it. In fact, till today, the brain signals were measured by what is called a superconducting quantum interference device, a SQUID. And these magnetometers can pick up very, very tiny changes in the magnetic field closely located to the SQUID apparatus. However, if you look at this gantry, I mean, this case, everyone, of the cost goes up. If you take an atom and do the same thing, as I said you before, by putting it close to an oscillating B field, you end up in a magnetometer which shows like this, and you don't need to freeze any or go down in temperature. You don't need a refrigerator at all. Now, this is again something which is being commercialized. Now, what I am going to tell you next step is that as we go ahead, you can actually combine different knowledges. For example, you can have a quantum sensor and you have a classical computer. Depending on the output of the quantum sensor, you prepare your next measurement and you continue feeding back your quantum sensor. If you do that, what we showed recently is that you can actually beat even the even the quantum limit, which is shown by the red line here. So what it shows here is the precision with which you can measure. So sensitivity of your measurement. And this is the time along which you take the measurement. So if you look at any point in time over here, our sensor even beats the presently known standard quantum limit. And these are sensors which are formed from atoms, which we trap in ion traps, exactly the same technology as is used by groups like, or companies like IonQ or Honeywell. These are called the ion trap quantum computers. It's exactly the same technology running over here. Now let's look into more dramatic thing, which is gravity sensing. So here is a model which shows that the water, as it drips into the Earth's surface, it gets collected in aquifers. And these aquifers can be at a depth of 20 meters or more. Some of you may have seen this, which is the east-west metro line in Kolkata, which is by itself engineering feat. It goes below the Ganges and comes up. However, at the end of the tunnel, it hits something like an aquifer, as in example here, because it was not known there is an aquifer. And you have seen the devastation it has caused and the amount of price that had to be paid. Thousands of people were displaced. The project is still on hold and the cost is escalating. And the reason behind this is not detecting aquifer, which is, by the way, is very difficult to detect. However, as we know that the quantum gravimeters, or in this case, gradiometers, can actually detect some things in this region, which is given by this vertical line. All the classical ones would act over here. So there is a good chance of these to detect, and they at present are also mobile, as you can see on the right-hand side, a system which is developed in UC Berkeley, but also other groups, including our collaborators, are working on this similar technology, and we are also ready to move out from the lab. So last, as I said, as you can see, the power of both worlds is better than one world, and therefore there is an interesting issue here that if we combine systems, we get more, both in terms of the quantum volume as well as in terms of what we can do. Now here you can see, you don't need to get into the details of these. These are different types of systems which are physically qubit, realizable qubit. The most promising one at the moment are the ion trap and the superconducting ones. While we should also learn from our previous experience that all of them may not win the race. And we have to bet on some, or at least having a good idea of what we want to bet on. So depending on that, you can see the early one when I started my PhD, that was the NMR time. But we know by now NMR has no future, particularly looking into quantum computation. At this point of time, these look very, very promising, and particularly you should look into this, which is the qubit lifetime, and the other thing to look at is the qubit error rate. Of course, the atoms has an inherent advantage that the atoms, they don't change from one atom to the other. Therefore, the rates are very, very stable. So the error rates are very low. Now, if you could combine these systems as is done or in the research labs all over the world in different laboratories, you could gain by using the atoms as memory and superconducting qubits as gates. The other possibilities which we are actively looking at is the error fidelity. If you could combine even classically, having a classical computer combining the two hardwares were entirely different, you could actually gain in solving certain practical problems. And that's exactly what we are working on towards certain applications. At the end, I end over here by putting up this slide, which is a dream, that is by combining different quantum systems, which we are all working towards, you can actually create what is called a quantum internet. And that's why the whole thing is approaching. So if you take, for example, a quantum computer interacting with a quantum computer, also with a quantum link, that's very important, you would end up in having what is called a distributed computing. If you use a classical computer to handle these, you could actually have a quantum classical distributed computing, and so on and so forth. So if you combine a lot of these quantum systems together, one day we would be able to have fully functioning quantum network. I guess I am close to the
4 minutes, please.
And that's where I end with thanking my support from the wonderful team.
That's wonderful. Thank you so much, Professor Manas. You have saved us 5 minutes while you were talking. I'm sorry, I just thought that I'll flag the last 5 minutes for you. You still have more time. If there is anything that you wish to say, you're free to do that. And I am going to take an example that got taken by you about Kolkata and how the tunnel which went through under the Ganges and came on the other way. I think we have this problem in strategic tunnels that we're trying to do in Himalayas. The strata is unpredictable, and the depth to which you can predict what kind of strata is there, whether it is in the horizontal shaft or the vertical shafting that you do, you end up having problems. As solutions like this, if provided well in time, I think we will have a better understanding of the topography, the strata of the stone, and how and what machinery should be used, and therefore it will be more predictable than before. So thank you so much for this, and we have some questions along which have come through. They're pretty technical. So one of them was, what kind of RTOs is used to integrate hardware and its applications? So there are many more very, very technical questions. So what I'll do is I will get Professor Ashutosh Sharma, our chief guest, to address us now, and post his address, then we will pick up a few technical questions and try and answer those through all of you if we still have time left before we have to start the other session. So over to you, sir. Thank you once more for joining us, and it's over to you now, sir.
Good afternoon. Thank you, Mr. Sood, Dr. Chanana. I'm so happy that ASSOCHAM is organizing this very important meeting on a very important topic, and you have picked up, except me, all the very good speakers on this particular topic. So it should be of great interest. In fact, it's very heartening to see that we have nearly 300 participants, friends who are listening to us. This is not bad at all for a topic of this kind, you know, quantum technologies and stuff. I mean, it's hard enough for people to be encouraged by classical mechanics, and if we are looking at quantum stuff here, I'm so glad that you are doing it. I'm also so glad you are doing it because you see, historically, Indian industries not really based on knowledge. They were not so much based on what you know, but who you know. And I'm sure that things are changing going in the future, which is very heartening indeed. And so all the great speakers, I learned a lot. Thank you very much, Dr. Raghunathan, and then Dr. Rohini, Srivathsa, and Dr. Mukherjee, and everybody. Great learning opportunity for me indeed, because I don't know that much about quantum mechanics. I learned it in the first year Physics 101 in IIT. And so, Mr. Sood, we are on the same platform. I also learned it 40 years ago, right? And pretty much that. But even 3 years ago, I was pretty convinced that quantum is, the future is quantum. Without knowing anything about either future or quantum, I was very convinced that this is so. And this is based on a simple logic. It's my own patented, copyrighted logic. So, you know, we all know this saying about is predictions are very hard, especially about the future, which means future is uncertain, which means future is quantum. And so this can be mathematically proved, and indeed it would be so, because we come to the end of classical mechanics on many fronts. So as was correctly pointed out, that quantum, of course, technologies that we are discussing here is not only about quantum computing. Certainly, it's about quantum communication, key distribution, cryptography. It's about quantum devices, for example, sensors were very well discussed indeed. It's about, in fact, even quantum materials, and you know, superconductivity is a good example of that. So you cannot get superconducting materials unless you have, in a sense, I mean, quantum states are aligned, and which is also very much the objective in quantum computing. By the way, thinking of that, it's very interesting that none of the speakers actually talk about quantum, maintaining quantum states in their coherent, you know, state, which is really the hard problem. So quantum computing is a hard problem, but was correctly pointed out that at this moment, quantum is hybrid. So we are looking at not just this very ideal pure quantum computer of very large capacity. That's indeed a hard problem, because it's a hardware problem actually. And so therefore, the Microsoft's approach, a lot of approach, which is based on hybrid and also based on simulation. So quantum simulators and stuff, that's something going forward. Now, in fact, my latest introduction to quantum technology, in fact, quantum, just 2 days ago, I was reading this book, which I had read about 30 years ago. But then I said, look, I mean, I don't know what I really understood 30 years ago. Let me pick this up again and have a go at it. This book is one of the classics of Mahayana Buddhism. It is called Lankavatra Sutra. Together with Mool Madhyam Karika of Nagarjuna, a classic text of Mahayana Buddhism. Now you may wonder, oh, well, what has that got to do with quantum? See, the final quantum frontiers going in the future, to my mind, it's about everything that machines cannot do, right? And so with the rise of intelligent machines, artificial intelligence, machine learning, deep learning, there's another story. We just started a big program on that. But what are the really fundamental problems of people? These are, of course, the riddles of perception, of reality, and consciousness. And quantum in each one of these plays a very significant role. Some of it is started working on, and I'm sure that there would be a very great, bright future. You know, the best of minds working on it. Now, it's very interesting. So I just picked up one sentence there. It said, don't say I exist. Don't say I do not exist. So that sounds a lot like the quantum state, which is a little bit undetermined and hanging in balance, like the Shanku we know right now, neither here nor there. But it's even more profound. It goes a little bit beyond quantum. So it says, do not say I exist and do not exist simultaneously. It also said, do not say I exist or I do not exist. Right? So it covers all the possibilities you see which are offered by the classical Boolean logic, right? And this is truly quantum. or you would say, para quantum, so to say, right? So by the way, the times that we are living in now, these are, some people say they are not normal times, so I call them paranormal times. So that could be one way to look at it, all paranormal. So anyway, enough gossip. I think I should get down to the business and say, okay, what is it about that we are talking? So it's about industry. So there are two things I want to cover very quickly. How do we bring in industry in all of this, because it looks very exotic. I mean, it's very hard to convince industry even to put in a crore in classical mechanics, right? I mean, to make a machine better, for example, right? So how are you going to actually get them on board on something which is as exotic and is promised being a little bit longer term in most cases as quantum technologies? Quantum, you can say about quantum science, but even technologies. And of course, they cover a very wide spectrum. Now, I mean, the first hints of quantum actually came with nanotechnology. So while I started as a chemical engineer, which basically means you are very way down in pecking order of science, but then I upgraded myself when the nano mission came around about 20 years ago. I said, hey, I want to become nanotechnologist. Right. So now at that time, anything was less than 100 nanometer is called nanotechnology. Today, we have shrunk the size of, research transistors to about 3 nanometer, and commercially 9, 6, something like that. Right. Now, if you shrink it any further, clearly you would run into some quantum things, right? Some beast. And then people are talking already about a single molecule, devices and so forth. If there's a small molecule, right, then clearly you're going to have this quantum molecular effects and so on. So it's very good. I mean, the future looks very bright in terms of getting into quantum domains. Now, coming down the size of electronic devices is one aspect of it, but a whole lot of nanotechnology is going to transform or start overlapping into the quantum domain. Right. So until now, less than 100 nanometer, you could extend classical mechanics in some ways. I mean, patch it up, so to say, and still live with your life and design things and so on. But it's getting more disruptive. So, so when I said like 3 years ago, I was convinced about the future being quantum. We started a new activity in Department of Science and Technology, a new division that we call, frontier technologies. Frontier and futuristic technologies, both of them have little different meanings. So frontier technology simply means that you are right at the front, at the forefront, and you are moving with it as it's developing. Now, the futuristic technology may mean you have a hint of it, but you can't quite see the frontier. I mean, because the frontier has not been established yet. And so while we have not gone to truly futuristic technologies, which, like I said, things related to perception, consciousness, reality, the nature of all of this, they would come about in 20 years when you have greater integration between the biology, the biological entities, and the machines. So now we talk about Industry 4.0. Industry 4.0 is the convergence of cyber and physical, digital, right? So communication, computing, decision making, perception in the sense of sensors, collecting data, making decision, and acting on it.
So you've gone mute, sir. Could you just unmute yourself, please? Professor Ashutosh, you've gone mute. Could you just unmute yourself? Okay. Are you able to hear this, Mr. Chanana?
No, we are. Sir, you are on mute.
Frontiers program is basically.
We actually just lost you in between. Your system went on mute. Go ahead, sir.
Oh, can you hear me?
Yes, sir. We can hear you.
And so you logged me. What part did you miss out? Can you tell what you could not hear? No. Okay, well, block like that. Okay, well, all
Yes,
right.
yes. Hello.
Yeah. Okay, well, right. I think it's okay. As long as you can hear me, you don't have to see me. But
no, sir, we lost you again.
is everything okay? Can I go ahead?
Yes, please go ahead. Can
Oh,
you
you
put
lost
everybody?
me. Okay.
No, that's fine. Put
I
everybody
think
on
if I
mute.
cut down on the. Yeah, of course, everybody should be on mute except me. Yeah, there's the first etiquette of webinars, as there's too much hassle going there. It will collapse our quantum state totally if we do that, right? So anyway, okay, now I don't know what I missed because I can't recall what I said, and you can't miss what you have missed, so you don't know what you're missing, so it's all right, we can go ahead with it. So I said, okay, this frontier technology program, we started first rolling out this mission on cyber physical systems. This is worth about $500 million. And so in purchase power parity terms and what, number of people you can buy with it and so on is maybe worth about $1.5 billion. So we are quite upbeat and positive on this. It has set up about 25 hubs. I will come to that in a moment because this is also going to be the architecture and the structure and processes of quantum technology mission are going to be borrowed from this. This is the first time I did really deep thinking, a lot of dreaming and stuff, and said we need a different way of doing business, right? Because, and I'll tell you why and what the unique aspects of doing this is, and how this would translate into our quantum technology mission, and how this would be empowering for the industry to work together. Right, so let me start on that particular theme. And so the first mission, which is cyber physical systems, basically there are these 21 hubs and 4 research parks. Right, research parks are the front end, basically interfacing with the market. So we want companies, like if you have seen the research park in IIT Madras, right? So that companies can move in there, they can interface with the researchers working in all of this. Now let us focus on the hub, because hub is the basic element of working on this mission. A hub, unlike the previous centers that we used to establish in different things, a hub is actually a holistic entity. What that means is it starts from basic R&D, but it also has technology development. It also has human resource generation, training at different levels. It also has all translational research. It also has an incubator attached with it. And then it has interface with the research part as well. So basically the entire knowledge chain, from knowledge generation to knowledge consumption, it must be met in the same broad set of people, as well as the processes of the hub, and so working kind of seamless. It's not necessary the same person has to do basic R&D and the technology and startups and industry. No, but point is that this hub is given all the flexibility and all the powers delegated to it, all the powers that I have, and some of the powers I don't have, which I took from the cabinet and passed on them to the hub. Because oftentimes people say, look, we don't, these are all sarkari things. We can't really do our business. You can't tie our hands and make us dance, right? It's not fair. I agree, it's not fair, right? So now these hubs actually, which are Section 8 company, right? They manage with their own board, their own business. They can make any kind of MOU with any industry. They can give money to industry. They can receive money from industry. They can take problems from industry. In fact, the board of these hubs, it has 1/3 representation from industry. So therefore, they're equal partners. 1/3 from the government, which means line ministries, 1/3 from academia, R&D labs of the government, and 1/3 from industry. So they together decide actually what are the problems which are worth doing, what kind of partnership would industry bring in, so all these things are there. the only interface that me or the government DST would have with these hubs is in the form of an apex mission committee. Mission committee is not headed by another Sarkari man like me, but is headed, for example, for cyber physical systems, is headed by Chris Gopalkrishnan, right? Or some similar person we would get for quantum mission, which is even more ambitious, is worth about 8,000 crores announced in the last budget. So I suppose as we come out of this time of Corona, then we think about quantum, right? So it may get little bit slow start and delay. We're all ready to start it because this DPR and stuff has been nearly completed. Actually, so we mapped all the people who are working in the area of quantum in the country and all the groups and all the people and bring them on board. So they write some part of the DPR, detailed project report. And so that all the aspects of quantum are in there, then we'll see like what has the greatest potential to develop. So we need three different kind of things: short term, medium term, long term, and they are all with the participation and partnership of industry in whichever form, because they don't have to deal with us at all. They just go to hub and work with scientists. You can put your own manpower there to solve your problems. Idea is that you can leverage all the resources which exist in the hub. Now these resources, they are human resources and they are infrastructural resources. So I mean, it's not so bad because if we had like 4 major hubs, which may be communication, computing, devices, stuff, 4 or 6 of them, whatever, so that we have this. So each one of them are worth about 1,500 crores or more. So that, to begin with, I mean, begin with meaning next 5 years or so, if we can purposefully use these resources, that would indeed do great things, because if things are working out, if things are developing in the right direction, I'm sure that 3 years, 5 years down the road, we would not have constraints on further resources, right? So this is actually a very different model, you see, of doing things, the architecture, the structure, and the processes of implementing something. It is very different because now is driven by the vision of people, the leadership at the hub level. They must be aggregators of the knowledge in their area across the country. They must also be the drivers of what activities should take place in that particular area in the country. So in other words, if I have to describe a hub in one sentence, then I would call it a mini ministry of area XYZ, which means that everything, giving a call for proposals, choosing proposals, making a big picture about where you want to be, then breaking that big picture into like a jigsaw puzzle, and then giving the little pieces to different people to work on, then reassembling these pieces to make the big picture. All of this is not the job of the government. All of this is the job of our scientific community working together with the industry, right? So if they are the custodian and aggregator of knowledge in that particular area, then this is going to work like a one-stop shop for your things, right? They also would have power to make MOUs with the foreign entities, right? And bring, let us say, a professor from abroad at his, at global salary or whatever, right? So all these powers are given to the hub. Because a Section 8 company, of course, they should do everything, proper accounting and audit and all that stuff. That goes without saying because it taxpayers' money, right? But the whole point is that they don't need to run up anywhere and get files moving and stuff like that. In fact, the cyber physical systems is the first time I've seen in my life, or any bureaucrat has seen in his or her life, that a file for releasing, let's say, 200 crores has not gone through our finance division. Okay, so these are beasts actually. But now the point is, when you shift all of this, responsibility to another entity, that entity has to be fully enlightened. Okay, so now you see the weakness is that we would have on the level of an IIT, on the level of our academia industry interaction, while many of them would disappear, and we have addressed them at least in a formal sense, but that vision is saying, look, that I have to work beyond myself. You see, see, our major model of doing science is competition. It is not cooperation, right? So I'm just bringing in another dimension here to think about. So, you know, by nature, scientists are very self-centered, which is a good thing. I'm a scientist, I know that, because it's all driven by, you know, this deep urge to be creative, to have brilliance, to be better than your neighbor, to publish more papers, all of that, you know, which is good, because that's how you motivate, bring out the individual creativity and brilliance. But at the same time, there are many problems that we would have here in missions like this, which are beyond an individual, right? And this is something that wisdom of the scientist working with everybody, whatever you know is required to be done to arrive at something good, that wisdom, that culture has to develop. And I think industry has a big role to play in this. So while not stifling individual aspirations and creativity and brilliance, which you know are not encouraged in certain hierarchical systems, the whole question is, how do you leverage that? I mean, without killing it, you get it out, but at the same time, that people spontaneously, willingly come together to work for the greater purpose and greater good. And I think, you know, while I've seen that multinationals, of course, have been typically more enlightened about these things, because the culture aspect, I'm very convinced that Indian industry, even MSMEs, maybe not in the quantum frontier, but so many other things which are going on, they would all benefit by a dose of knowledge, right? So going forward in the future, we don't have an option. Look, if you want to be competitive, if the industry survival is based not on, like I said, who you know, but what you need to do, we have to make a transition to this sooner than later. And this is what our Prime Minister said about Atmanirbhar Bharat. So Atmanirbhar Bharat, to my mind, is not simply make in India. I mean, make in India manufacturing is one aspect, but it's a whole chain. And this is where industry comes in, because we have people from industry here. I'm very delighted that I can share some of these things, which I cannot share with academia and other people, right? Because you see, it's about manufacturing, but it's also about self-sufficiency. Means that you're also generating some knowledge, especially knowledge which is relevant, which somebody else would not generate for you. So generation of knowledge, which is in terms of R&D, then translation of that knowledge, the design, the prototyping, the startups, all of this ecosystem is part of that Atmanirbhar Bharat in the sense of science, technology, and innovation, right? And so these missions have in them, you know, incubators, startup nurturing, IP portfolio management systems, onboard venture capital integration, fund of funds, investment funds, and working with industry, right? Giving all of these flexibilities. So so I'm not getting into quantum. As I said, I'm not an expert. Of course, I read now and then, so I know the keywords like everybody else, right? But if you ask me to design something, then I'd be totally lost and not really know the micro details of any of this. But so okay, so I'm not. So I said it's not about quantum technologies. The thing that I'm discussing is more about, you know, how do we move forward in big areas of science and technology, and we do it not business as usual, right? And I would conclude by saying, right, I'm out of my time, isn't it?
So that's okay. You got extra 5 minutes.
I would conclude it. I just conclude it. Usually, I do repeat it, you know, to my younger friends. Usually, they are saying, "Hey, is this old guy talking?" So I explain to them that there is no such thing as old people in this world. I have never met an old person. There are young people and there are younger people, younger people usually, right? So all of us, anyway, it's a detour. So I explained to them that there are 3 ways of solving a problem, and these are in Hindi. I call them Jugaad, Dhanda, and Panga. So Jugaad, we all know, it is basically by hook or by crook. I need to solve a problem to be alive, to die another day, right? But today I have to move forward. I somehow have a pressing problem that I need a solution for. This solution may not be ideal. This may not be an optimal solution, but it would let me live for another day, right? And this may not be a scalable solution. So while we have to slowly move away from Jugaad, except for pressing problems, and have this mindset of quality and optimal solutions, of course it takes time to develop them and requires a foundational aspects to develop them. Second one is Dhanda, and Dhanda is this very stable, continuous operation, which means 2%, 5% growth next year. And this is what most of our business is, Dhanda. And I ask all my friends, by Dhanda acha chal raha hai? They say, very good, doctors are very good. Dhanda acha chal raha hai. Then everybody is happy. We go our way, right? And then Panga is these disruptive changes. And so many more of our young people have to be ready for these truly disruptive changes, whether it is in terms of their education, skills, acquiring new knowledge, new information, and making use of it. The future basically comes at us at a faster and faster rate, right? And then so we have to be part of that change, totally respecting the will of the future, so to say, and be integrated with it, which means risk-taking ability, which is not there in any of our educational systems or cultural systems or industrial systems or any of that, right? So certain amount of risk taking. I'm not saying Panga would be 100%, that would be itself a Panga. I mean saying Dhanda is the stable backbone of everything. But on top of that, if we put in 20% of Panga, encourage that in every form, that that we can do some pole vaulting instead of what it used to be called, frog jumping. No,
leapfrogging.
Leapfrogging, yeah. Who cares about frogs anymore, right? So we should go for pole vaulting scenarios and so on. 20% of it.
They're also saying orbit shifting, so that's kind of
orbit shifting. All right, yeah. So I mean, we're also in the space age, and so on. So that would make sense. Just don't shift the orbit of Earth very much. This is such a fascinating thing. We don't have time to talk about it. But if the Earth was out on either direction by few hundred kilometers, maybe life wouldn't be around. So there are things about orbit shifting as to how much disruptive you can be, and how much as a balance. So I would conclude by saying, just quoting the Mool Madhyam Karika of Mahayana, this is all about balance, right? It's all about there are no extremes. People who argue on extremes, people who argue on booleans will not find any solution ever. And this is why I'm so happy about quantum, and I'm so upbeat about quantum, and I'm so positive about quantum, that all the stuff we could not do by boolean logic, by on extremes, on the corners, this would not only help new technology, this also help new ways of thinking about us, about where we want to be. Thank you very much for such a patience listening. Thank you.
Thank you so much, sir. So enlightening to hear. Thank you very much.
The quantum mission, as it comes around, especially from industry. Be our partners. You would not be disappointed.
Absolutely not, sir. We will be part of it every way along with you. Thank you so much. Really, really appreciate it. I think what 90 days of lockdown has taught us and made the world and every human in the world accept, we would have not done it in 5 years. So there's a lot of change that has come through. So yes,
one of the things we need to do, because industry people are here, one of the things I always tell, look, this experience has to improve, because if this is going to be paranormal or new normal, right now, this experience we are having right now, this is based on 10-year-old technology. So this requires some disruption now. What I want to see myself myself is sitting with all of you in a virtual experience, right? So 2 years from now, if we meet, this experience should be more real, so to say, right? So we should all be able to determine what our meeting room is going to look like, and that we feel that we are sitting next to each other in a like 3D hologram or something. I don't know. I'm sure all these technologies are there, just a question of scale and cost, right? And little bit of thinking to put them together. I haven't any doubt that this is the future, and this future, if we can make it more realistic, then it would be more greater pleasure in terms of interaction and greater effectiveness of interaction, right?
Yes, certainly, sir. Before I get to Dr. Chana, very quickly, sir, I was part of a presentation that was made, and I think that's what you just mentioned. Tourism is going to head that way. So there will be physical tourism and there will be virtual tourism, and virtual tourism is real virtual.
Good old days. I went to one of your meetings. You gave me a nice flower bouquet. So I'm missing that. Maybe you send it to me, a virtual bouquet, to all the speakers. Right?
We'll do that, sir. Thank you so much. And I'm going to now ask Dr. Chanana to help us guide this. Thank you so much, all speakers. Dr. Chanana, over to you.
Okay, thank you, Mr. Sood. The last thing to do is propose the vote of thanks, and thank you, Professor Sharma, Secretary, Department of Science and Technology, for agreeing to be the chief guest today. This is the first quantum technology conclave that the ITes Council of ASSOCHAM is hosting, and we do, looking at the response and looking at the content that we had in terms of learning, we do hope to make it a kind of a repetitive exercise wherein we can actually come back periodically to understand the developments as we take. Thank you very much for highlighting some of the ministry's initiatives, sir, particularly the point that you mentioned about the 200 crores file not going to the ministry was like music to the ears. Thank you so much for that. We are all aware about the cyber physical systems project in terms of the work that is being done, and we look forward to this particular mission also going the same way, and we hopefully will establish our position, if not the supremacy in the quantum technology. Thank you, Dr. Shesha, for setting the context, and thank you for highlighting in the beginning itself the applications of quantum computing, particularly around, particularly for India. And thank you, Dr. Rohini, Srivathsa, for starting with the promise of quantum computing. And I love your last slide, which said that while the research is being carried on, let's learn from each other. So learning while we are actually this field is coming. Thank you, Dr. Mukherjee, for highlighting the supremacy of quantum and also the very interesting quantum computing manifesto. That was something that was something real for us. I personally feel, as IT Council of ASSOCHAM, we need to take this subject forward for us to be, because all of us are aware that several quantum technologies will now evolve and come to a commercial stage in the near future. Many industry players are already conducting research on sensors, metrology, imaging technologies, quantum communication, network, quantum cryptography, quantum simulators, or at least they intend to use and take advantage of this. Given this huge interest and given the huge potential, we look forward to such contributions in future. And this was a very, very interesting, and and the ASSOCHAM team needs commendable appreciation for the excellent work that they have done to actually organize it. Thank you very much to all of you for all the great words that you said. Thank you.
Professor Ashutosh, may I just take a minute, sir? Thank you so much, Dr. Chanana.
This link somewhere on YouTube or something.
Yes, sir. So this is going to go. This is recorded, but we put it on our website and also put it on YouTube and others.
Just send us a link.
We'll do that, sir. There's a lot of questions, so
I need to know what I missed talking. Okay, so thank you very much.
So, just take a quick minute with you, sir. The Section 8 company that you did mention about, and you spoke about 1/3 of the board being from industry. So ASSOCHAM represents a lot of such boards of multiple departments, and we are very happy if we are given an opportunity to be one of those organizations who can contribute significantly.
You see, what I explained to you, I would not be the one deciding as to what the board composition would be. Okay, so certainly, you know, all the if you have, let's say, if there is a hub, let us say on a certain thing, let's call it okay, sensors or something, but or robotics or whatever, right? So the companies that have interest in that particular activity, right? Basically, by talking to the people there and who comes on board and so on, so they are totally, I mean, free to determine the composition of their board.
Sure. So we'll try and position our technical people.
Yeah, go ahead.
No, I'm sorry, you were saying something, sir.
No, I just said the chairman, I mean, nominally, because we want these things to function in a particular, say, IIT or somewhere, right, with a building. So the director of there may become the chairman of the board, but the rest of them are, you know, with a dialogue.
Sure.
As to, you know, who brings what value to it.
Sure. So we will explore the possibility, because we have a lot of members and technical people, so they would be very, very keen, and they would be great people to get on rotation basis. So you'll be able to contribute much more than just one person sitting there. So that's what I will explore and come back to you, sir.
I agree. So if you had, for example, a representative of the association, and you know, that kind of connects that hub to the entire membership, that's also a good idea, right?
Wonderful, sir. Thank you so much, sir. Really appreciate it. Thank you very much.
Thank you. Stay safe.
Thank you, sir.
All the best.
And you, sir. I'll catch you very soon in office. Thank you so much. Varun, let's start the next session. I would now hand over to Aditya Chaudhary. Varun, is he already there?
Yes, Mr. Chaudhary, can you switch on your camera, please?
Yeah. You can see me.
Excellent. So you still see a hazy of you. That's clear now. So I'm going to sign out. Thank you very much. I'm sorry, I wanted to pass it off on time, but I've delayed your session by 11 minutes. Good luck to you. And I'm going to be listening, and my mic and my camera will be off now. Thank you.